Well, let's talk a little bit about using confidence intervals instead of point estimates. Now, if we take a sample, we get the mean of the sample. That's an estimator, an unbiased estimator of the population mean. But it's likely not to be right on it. So what we can do is we can put a confidence interval, a range that the population mean is in with a given probability. So remember our confidence intervals, we can establish a 95% confidence interval and say, well, we're 95% sure that the true mean is between this and this, is within that interval. The greater the variability of the random variable, the wider the confidence interval to be 95% sure. The larger the sample, the narrower the confidence interval. Now let's talk about the student's t-distribution. Student's t-distribution is similar to a normal in that it's symmetrical, but it has fatter tails than the normal distribution. It's a leptokurtic distribution. So fatter tails, remember we care about fatter tails because that means there's a higher probability of more extreme observations further away from the mean. Now, student's t-distribution is defined by a single parameter. Everything else is already determined. And that single parameter is degrees of freedom. And that's just our sample size minus 1. So as the degrees of freedom increase, our sample size increases, the t-distribution approaches the normal distribution. But for smaller sample sizes, when we use the t-distribution, we're doing that because we want to know the probabilities taking account of those fatter tails. And here's a graph that gives you an idea. We've got our fatter tails here for the t-distribution compared to the normal. And you can see with degrees of freedom equal to 100, it gets more and more like the normal distribution. So by the time we get to 120, 200 observations, so our degrees of freedom would be 199, we're very close to the normal distribution. So greater probability of extreme outcomes compared to the normal, and because of that, wider confidence intervals. We've got more probability out in these fat tails, so our confidence interval, remember for the standard normal it was plus and minus 1.96 standard deviations. Well, with the t-distribution, maybe it's 2.14, for example. And so we'd have a confidence interval instead of 196 to 196, it'd be just a little bit wider. Remember, for a 95% confidence interval, we want to leave 2.5% in each tail. So these tails have to get smaller because of the greater probability, because we have those fat tails. So let's build a confidence interval here. We want a confidence interval for a random variable. We're going to take the point estimate, and then we're going to go plus or minus this reliability factor times our standard deviation, or in the case of a mean, the standard error. So consider a normal distribution with mean 3 and standard deviation 2. If we want a 90% confidence interval, we're going to take the mean, and then we're going to add and subtract 1.65 standard deviations to get this interval right here. So for that random variable, 90% of the outcomes are going to be between minus 0.3 and 6.3. And if we want a 95% confidence interval, we'll have to go a little wider to get 5% more, and that's at 1.96 either side of the mean. Now if you look at this table here, this refers to when we need to use the t-distribution. And it looks a little complicated, but it's not too bad because we've got a t statistic here. That says if the variance is unknown and our sample is small, but we're sampling from a normal distribution, we need to use the t-statistic rather than the z-statistic. Now, the t-statistic is also appropriate when our variance is unknown. And the reason for that is when our variance is unknown, we've got to estimate it from the sample. And that puts a little more uncertainty in there. Okay? We're estimating the standard deviation. We don't know it. So since that's an estimate, we've got to go a little wider to get our 90% or our 95% confidence interval. Now, these little asterisks are here because in the CFA curriculum, it says the z-statistic is theoretically acceptable here, but use of the t-statistic is more conservative. So we really only have one spot here where it says we have to use the t-statistic. Anytime the variance is unknown, it's more conservative to use the t-statistic. And the only other area we've got here is not available. So if we don't know the distribution, and any distribution where we're not told that it's normal, we consider that not normal. So if it's an unknown distribution and we have a small sample, we can't say anything. So if I've got numbers on the balls in the barrel, and I don't know that they're normal, I don't know what the distribution is, I take a sample size of 25, I can't really put a confidence interval on the mean. So we've got not available, small sample size, and non-normal, that is unknown distribution, or known and not normal. And in the rest of the cases, except for small sample size, normal distribution, and unknown variance, a z-statistic is theoretically acceptable. So let's do some examples here. We've got a normal distribution with known variance. The sample mean is 80, the population standard deviation is 15, and our sample size is 36. Establish a 99% confidence interval for the population mean. Well, we've got a good sample size here. We're given the population standard deviation, so no worries there. So we can use a z-statistic here. So our z-table reliability factor, remember for a 99% confidence interval, is 2.58. And what this notation means here is this alpha, which is 1%, right? If we've got a 99% confidence interval, then what's outside of that? Well, 1% is outside of 99%, and if we divide that by 2, that's the probability in each tail outside this confidence interval. Now we calculate the standard error of the mean. We've got the standard deviation of the population is 15, so we divide that by our square root of our sample size, n, and we get 2.5. So we want a confidence interval for the mean. And the confidence interval for the mean is based on our sample size. And so we've got 2.575. We used 2.58 earlier for our reliability factor here. And then we put in not the standard deviation of 15. We're going to put in our standard error. Because it's a confidence interval not on a single observation, but on the mean of 36 observations. If we wanted a confidence interval on a single observation, we'd use the standard deviation of 15. But for a confidence interval on the mean of a sample of size 36, it's much narrower. So mean plus or minus 2.58 standard errors gives us this range from 73.55 to 86.45. Now we've got a normal distribution with unknown variance. Our sample mean is 2%, sample standard deviation is 20%, and n equals 30, our sample size. Now we want a 95% confidence interval for the population mean. So we're going to take the mean, because it's 95%, we're going to go 1.96 standard errors either side of that to get our 95% confidence interval. But we can also do this with a t-distribution, because our sample size is kind of right on the line. Okay. We've got sample standard deviation. We don't know the true standard deviation or variance of the population. So that falls into one of our boxes, the t-distribution with a little star by it. So let's do this with a t-distribution. Our t reliability factor, now you can see this from the t-table in the back of the Schweizer Notes book for quants. And so we go down to the degrees of freedom, 29, and we want the column, we want to put 2.5% in each tail. And so 2.5% in each tail, 95% in the middle. And remember our fat tails with the t-distribution. So our reliability factor is a little bit larger. Remember our 95% confidence interval was 1.96 standard deviations for a normal, but because it's a t-distribution, the tails are a little fatter, we've got to go a little bit wider. And so we have a standard error of the mean. There's our standard errors. So we're going to go plus and minus 2.045 standard errors instead of 1.96 standard errors if we're using the t statistic here to establish our confidence interval on the true mean of the underlying distribution. So let's contrast those two ideas, because I know this is something I get a lot of questions about over the course of a term. Let's say the annual returns on energy stocks are approximately normally distributed. They got a mean of 9% and a standard deviation of 6%. Now our first task here, construct a 90% confidence interval for the annual returns of a randomly selected energy stock. Well, 90%, our reliability factor is what? It's 1.65. And it's a single observation, so we're going to use the standard deviation of 6%. And got a mean of 9. So we're going to take 9% plus or minus 1.65 standard deviations. The second one says construct a 90% confidence interval for the mean of the annual returns of a sample of 12 energy stocks. So we're going to get a narrower confidence interval for the mean of 12 than we do for an individual observation. So now let's look at that one. Well, our reliability factor for 90% confidence interval is still the same, 1.65. The mean's still the same. What's different is we're going to use that standard error there instead of the standard deviation. So we divide 6 by the square root of 12, and you see we get quite a bit narrower confidence interval for the mean of 12 than we do for a single observation. So when the mean is involved in this test or this confidence interval, that's when you want to use the standard error. Now, there's some issues with sample size. Overall, what we looked at so far suggests to us, hey, bigger sample size is always better. If we had more data, we'd have narrower confidence intervals, we'd be more sure of the range of values the true mean might take. But there's a couple of limiting factors on sample size. And one is that cost can be a factor. Just obtaining more data can increase costs, but oftentimes data has to be manipulated and scrubbed and cleaned up before you can use it, and that all imposes costs as well. So there's a trade-off between sample size and costs. The other situation where a larger sample size may present some issues is that if the population has changed, if the distribution has changed. So say I'm looking at pre-World War II data, and I estimate the parameter, the mean of a distribution. And it turns out that after World War II, things had changed in financial markets so that that wasn't really the mean anymore. Well, in that case, adding more data to our pre-World War II sample isn't necessarily going to make our results any better, because now we're adding data from a distribution that has a different mean or perhaps a different variance. And so there, adding more data doesn't really help us because that data is not from the same underlying probability distribution as our original sample. So some types of bias in sampling and estimation. First off, data mining bias from repeatedly doing tests on the same data. Well, we've got to have, probability is always involved in our inferences and statistics. We're never certain of anything. We're making probabilistic statements, inferences, confidence intervals. Well, that means that we're going to be wrong. If our confidence interval is 95%, we're going to get a sample mean outside of that 5% of the time. So if we've got a lot of researchers working on the same data set, like securities prices over the last 75 years, when they establish these confidence intervals and test hypotheses, they're going to get wrong results 5% of the time. So what this means, the data mining part, is if you keep going back to the same data and test and test and test, 5% of the time, you're going to get bogus results. And if you hang your hat on those, you're going to be disappointed. Sample selection bias, well, if the sample is not really random. Remember, random, every member of the population has to have an equal chance of being selected. If that's not the case, our sample is going to be biased. Our sample mean is going to be a biased estimator of the true mean. Survivorship bias, sampling only surviving firms, mutual funds or hedge funds. When we get to alternative investments, we'll talk more about this with respect to hedge funds. But you can think of it with mutual funds. Say I'm a researcher, I want to do a test on mutual funds. I want to look at their mean returns, I want to look at their distribution of returns. And I say, well, I need at least 20 years of data. I need 80 quarters of data. And so I go out and I find a lot of mutual funds that have been around for 20 years so I can do my test. Well, right there is the problem, because those are all funds that survived 20 years. The better thing to do would be to look 20 years back in time and say what funds were available and then track those going forward. Reason being, funds that survive are ones that did relatively well. Mutual funds that don't do well, they get wrapped into other mutual funds, they get renamed, they get closed down, they disappear, they don't survive. So choosing them at a point in time and looking back 20 years is troublesome. Going back 20 years and saying what funds were available at that point in time and then following their returns forward over that 20-year period is the way you need to do it to avoid survivorship bias. Look-ahead bias refers to using information that wasn't available at the time. So maybe I look at book to market value, market price versus accounting book value. And I find that, well, if I built portfolios starting January 2nd each year, based on the book to market value rank of them at the end of the prior year, I'd be doing look-ahead bias because I'm forming my portfolios on January 2nd, whereas the accounting statements for firms, they don't come out on December 31st, the date on the balance sheet. It takes them a while. They're released maybe in March, maybe in April. So I'd be forming portfolios based on information that wasn't even available then. That would be look-ahead bias. And time period bias says, well, the relationship exists only during the time period of the sample data. So I had some data, I did a test, I found a very strong relationship that I thought I could exploit in security markets, but it turns out outside of that time period, the relationship didn't exist. So I've got time period bias.